Problem 1 is about polar coordinates. We have the function r is equal to 2 plus 2 times the sine of theta. Theta runs from 0 to 2 pi. We want to plot this. The easiest way to go about it is probably just to choose some easy values of theta for which we can evaluate this easily. So typical choices will be some rational multiples of pi. And let's first plot these points. Okay, if theta is 0, then the sine of 0 is 0. So r is equal to 2 plus 2 times 0. So for theta equals 0, our radius is 2. For theta equals 0, this goes in this direction. So that's the first point. Next, let's look at theta equals pi over 2. We know that the sine between 0 and pi over 2 is strictly increasing, so our radius will increase. We don't get any other wobbles in there. For theta equals pi over 2, the sine is equal to 1, so our radius is equal to 2 plus 2 times 1, which is 4. So this is this point because up is angle pi over 2. Next angle pi, this goes to the left. What do we get there as radius? Well, the sine of pi is 0. So we get, with the same argument for theta equals 0, we get radius 2. However, now it goes in the other direction, so we get this point. Finally, 3 over 2 pi, the sine is minus 1. So 2 plus 2 times minus 1 is 0. So we get this point actually in this direction here, where theta is equal to 3 over 2 pi. We start at this point here for theta equals 0. Now up to theta equals pi over 2, the function is strictly increasing because the sine is increasing. So our function will look something like this. Next, sine is decreasing, so we decrease in the radius until we get to the radius 2. Sine furthermore is decreasing, so our radius gets smaller and smaller. So we get this, and again our radius gets smaller and smaller, and we get this. Okay, this is not a very good plot, but it shows roughly the behavior of the function, and this is certainly good enough for what we would expect in an exam. Part B asks about the area enclosed by this curve. For this, it's useful to get an estimate first of how much area do we actually expect. This way we can check our result, and since we have plotted it, actually we can use that plot. Well, our plot was not very good. Using a calculator, I've tried here to draw it a little bit better. Now if you look at the area, the graph is obviously symmetric along this vertical axis. So if we try to count area, this is 1 unit, 2 unit, 3 unit. This is a little bit less than 1. 4, 5, 6, 7. This is about a half. This is another half, so we have 8. This here and this here together, let's count this roughly as 9, and with this 2 other halves, so about 10 and twice. So we would expect that our area must be somewhere around 20. This is a very rough estimate. We know the formula for the area from the lecture. The area is the integral over the angle range for which we are plotting. We are plotting from 0 to 2 pi. And we have to integrate over 1/2 r square d theta. R now is r of theta, so in our case this is the integral from 0 to 2 pi over 1/2, 2 plus 2 times the sine of theta squared d theta. Well, let's simplify this. This factor 1/2 we can pull out, so we get 1/2 times the integral from 0 to 2 pi. Now let's expand 2 plus 2 times sine of theta squared. This gives us 2 squared is 4 plus 2 times 2 sine theta times 2 is 8 sine theta plus 2 sine theta squared is 4 sine squared of theta d theta. Now you might have wondered, why didn't we kill this factor 1/2 with a symmetry argument as often done in the book? Well, we don't need to do this because we can kill this factor 1/2 also by dividing the 1/2 out from our factors here. Right. Now we want to find antiderivatives. Well, the first steps for this are very easy. Antiderivative of 2 is 2 theta. Remember, we integrate with respect to theta. Antiderivative of 4 sine theta is minus 4 cosine of theta. Next, the antiderivative of 2 sine square of theta. Well, we get a 2. Now, we probably don't remember the antiderivative of sine square, but what we can do is we can look up from the front of the exam the double angle formula. This told us that the sine square of x is equal to 1 minus the cosine of 2x divided by 2. So we get the integral from 0 to 2 pi over sine square of theta is now 1 minus the cosine of 2 theta divided by 2. Okay, and the 2 can cancel with the other 2, and of course we stay d theta. Okay, copying the terms to theta minus 4 cosine theta. Oh yeah, here we had the integration limits. I had to write 0 to 2 pi minus 4 cosine theta plus antiderivative of 1 is theta, antiderivative of cosine 2 theta, antiderivative of cosine is the sine, so we get the sine of 2 theta, and to make up for this factor, inner factor 2, right, derivative of sine 2 theta would be 2 times cosine 2 theta, so we need to make a factor 1/2 here, and this goes from 0 to 2 pi. This is 3 theta minus 4 cosine theta minus 1/2 sine of 2 theta in the limits of 0 to 2 pi. Now we could evaluate all these terms separately. That would be, which isn't that hard, but would be a lot of terms to write down. But let's notice something. We notice that cosine theta has the same value at 0 and 2 pi. Similarly, sine of 2 theta has the same value as at 0 and 2 pi. If we evaluate this at the upper limit at 2 pi, we get the same value as when we evaluate this at the lower limit, and therefore these terms will cancel out. So this must be the same as 3 theta evaluated from 0 to 2 pi. And that's now very easy, namely that is 6 pi minus 0, which is equal to 6 pi. So we calculated this for the area. What is 6 pi? Well, pi is 3.141, so this is a little bit more than 18, something around 1819. If we go back and we look at our estimate, we had estimated something around 20, very roughly. And that looks right. So not only do we have the area calculated, we also have a somehow independent verification that the value we got is not completely wrong.